Okay, so today we are going to talk about protection of carboxylic acid and alkynes. So today's focus is on carboxylic acid and alkynes. So let's begin with carboxylic acid functional group. So the first method to protect carboxylic acid, so this is my carboxylic acid. And if you want to protect it, you need to convert it into an ester. And the reagents we are going to use a alcohol under acidic medium. So that's all you need to convert your carboxylic acid into an ester, a alcohol source and acidic medium. So what is the mechanism? So we have a carboxylic acid and we have an acidic medium. So these oxygen lone pairs will grab this proton and we have an activated carbonyl system now. Now at this point of time, the alcohol molecule will come. This oxygen lone pairs will attack at this carbonyl, will open up this C double bond O bond, and we have singly bonded OH, another OH, and we have recently joined this carbon with this oxygen. So we have O, H and R dash. So this oxygen have 3 bonds, so we'll get positive charge. Okay, now the intramolecular hydrogen transfer will take place, neutralizing oxygen. So this will give me R, OH. Now this OH is OH2. So it will get a positive charge, and here we have OR dash. Okay, now this oxygen lone pair will form a double bond here and will eliminate water molecule in its neutral form. So now we have R, C double bond O, H with positive charge, and we have OR dash. Now whatever water molecule has just left will come into picture. It will act as a base this time and it will grab this proton, neutralizing oxygen. And this is how you will get your final product. So this is the first method to convert or to protect your carboxylic acid into an ester by using alcohol under acidic media, and this is the mechanism for it. So now let's move forward and see the second method available. Okay, so let's see the second method. So in second method, we'll start with carboxylic acid, and first we need to convert it into a acyl chloride. And to do this change, you need a thionyl chloride, SOCl2. So SOCl2 will convert your carboxylic acid into a acyl halide. Here we have a acyl chloride. Now, for the second step, you need an alcohol with a base. Base you can use like triethylamine, or maybe you can use pyridine as a base. And this will generate the product we are looking for, that is the alcohol. That is an ester. So what is the mechanism for this second step? So we have alcohol and we have a base like triethylamine or pyridine. So that base will grab this proton and will generate an alkoxy anion. And once you have an alkoxy anion, it will react with your acyl chloride. So this oxygen will attack at this carbonyl, and through conjugation Cl is going to leave, and this is how you generate the ester molecule. So this is the second method to protect your acid into an ester. In first step you need to use thionyl chloride and you need to convert it into acyl halide, and later you need to use a base with alcohol to get your ester, and this is the mechanism for it. So now let's see the third method available. Okay, so for the third method, you have an acid. You need to use a base. Let's write triethylamine with a alkyl halide. Okay, you can use iodomethane or anything, like any alkyl halide source you have to use, and that will convert my acid into an ester. So what is the mechanism? Well, mechanism is pretty straightforward. I have a carboxylic acid. I have this very acidic proton. I'm using a base that will take away this proton, will generate a carboxylate anion. And once you have an anion, and when you will react it with alkyl halide, it will attack at this alkyl carbon, will eliminate the iodide anion, and this is how you generate the ester molecule. So this is the third method to protect your acid into an ester, by using triethylamine as a base to abstract this proton and generate this carboxylate anion that will be later attacked to this carbon of alkyl halide to generate ester. So this is the mechanism for it. Okay, now let's see the fourth method. So you have a carboxylic acid and you want to protect it by making an ester. Let's make the methyl ester. So here all you need is a diazomethane to bring out this change. What is diazomethane? So the complete structure of diazomethane is like you have a CH2 double bonded with N, double bonded with N. This center nitrogen gets positive charge, this terminal nitrogen will get negative charge. The resonating structure can be, so this nitrogen lone pair can form triple bond here, and this double bond lone pairs or bond pair will collapse on carbon. So the resonating structure will be CH2 negative N triple bond N with positive charge. So this is the reactive form of diazomethane, and you have a carboxylic acid. So this proton is very acidic. So this CH2 minus will take this proton and will generate carboxylate anion. So you have a carboxylate anion, and now you have CH2 converted into CH3. So you have a CH3 singly bonded with N triple bond N, and this can be written as N2 plus. Now this oxygen minus will attack at this carbon and will eliminate N2 as a gas. And now you have formed the product OCH3. So this is another method to convert your acid into an ester, particularly a methyl ester, by using diazomethane as the reactive intermediate. And this is the canonical form of it, where this CH2 minus will take this acidic proton, will generate carboxylate anion that will later attack at this carbon, eliminating N2 gas to form your product. Okay, now let's talk about the fifth method. So suppose I have a carboxylic acid. I'm reacting it with alcohol, DCC and a DMAP, and this is giving me the ester. What is the structure of DCC? Well, DCC is what we call the dicyclohexyl carbonamide, and structurally it can be written as, so you have a cyclohexyl group bonded with nitrogen, doubly bonded with carbon, doubly bonded with nitrogen, and once again a cyclohexyl ring. So this is the structure of DCC. And what is the structure of DMAP? DMAP is dimethylamminopyridine. So you have a pyridine and you have a para substituted dimethyl amino group. Well, DMAP is a base. You need to know that DMAP is a base. But sometimes it can act as a nucleophile with this nitrogen lone pairs. So feel free to pause the video and try the mechanism for this reaction. Okay, so let's begin. So we have a carboxylic acid and we have a DMAP, which is a base. So this DMAP will act as a base, will take this proton, will generate a carboxylate anion. So you have O minus. Now you have a DCC group. For time being, I am representing this cyclohexyl group with CYX and double bond C, double bond N, CYX. So this oxygen with its negative charge will attack at this carbon, and this C double bond N will collapse on nitrogen. So this will form cyclohexyl, N double bond C, single bond N. This N has a negative charge now with CX, and this carbon is bonded with oxygen, C double bond O, and a R group. Okay, now the side product of this reaction was this nitrogen bonded with hydrogen. Right, and this nitrogen having positive charge. So this nitrogen lone pair will take this proton and will neutralize the nitrogen. So you have CX, N double bond C, single bond NH, cyclohexyl, and you have regenerated your DMAP. From where we are getting this? The byproduct of this reaction, where N is taking up this hydrogen. Okay, and we have this. Now at this point of time, once again the DMAP will come. Now this time the nitrogen lone pair are not acting as a base. Instead, it's acting like a nucleophile. So it is attacking at this carbonyl through resonance. This CO bond will form a double bond here, and this C double bond N will be taken by the H plus source. So what is the product we are getting? So here we have cyclohexyl, NH, C double bond O, NH, and cyclohexyl, right? Cyclohexyl, NH, C double bond O, NH, cyclohexyl. And other product we are getting is, let me write in a different page. So this is my one of the product, and the other product will be this nitrogen bonded with this carbonyl and this R group. So the other product is RC double bond O, nitrogen. Basically we have attached DMAP with our reactive species, and here we have a positive charge. So this nitrogen is now bonded with this RC double bond O, and this is what I have written. This nitrogen is bonded with this RC double bond O. And finally we have alcohol. Now this will come into picture. Will attack at this carbonyl, and through conjugation this whole group is going to leave in a neutral way, and this will give me RC double bond O, OR dash. Okay, so simply we connected this carbonyl carbon with this oxygen, and this whole DMAP will again leave out in its neutral form. So DMAP is playing a crucial role in this reaction. It is acting as a base also, and it is acting as a nucleophile also. And DCC is another reactive species we are using in this reaction. Okay, now let's talk about the sixth method available. So I have a carboxylic acid, and if I react it with alcohol, PPH3, and reagent called DED. So this will give me the ester molecule. So what is the structure of DED molecule? So DED stands for diethyl azodicarboxylate. So the structure of DED molecule is like this. So we have a diethyl azo dicarboxylate because it is an ester molecule. So feel free to pause the video and try the mechanism for this reaction. Okay, so first this PPH3 and DED will react among themselves. So we have a PPH3, so its lone pair will attack at this nitrogen, and this double bond will fall on nitrogen atom. So we have CO2 ET, nitrogen bearing negative charge, singly bonded with nitrogen. We have another CO2 ET, and we have a PPH3 now. Now this phosphorus will get positive charge because it's forming 4 bonds. Now we have an acid, and we have a negative charge. So this negative charge nitrogen will grab this proton and will generate carboxylate anion. So we have E80O2C, and we have NH, nitrogen, CO2 ET, and we have a PPH3 bearing positive charge. And we have also generated the carboxylate anion. Now the alcohol will come and this alcohol is going to form a bond with this phosphorus, and this bond is going to break and fall on nitrogen. So now we have ETO2C NH, N bearing negative, another CO2 ET, and we have also PPH3 bonded with oxygen, hydrogen, and R dash. So this oxygen will get positive charge. This phosphorus will also get a positive charge. Now this nitrogen lone pairs will neutralize this oxygen by grabbing this proton. So now we have R dash oxygen bonded with PPH3 having positive charge. Okay, so now at this point of time I need to write it in a full structure form. And the byproduct here we are getting is ETO2C, NH, NH, and CO2 ET. So till now we have generated this molecule, and we have formed a carboxylate anion here. So now this time this will come into picture. Excuse me, this is C double bond O, O minus, and in last step this O minus will take this alkyl group and will form double bond here. Okay, and this is how you will get the final product, that is your protected product. And what is the byproduct? Well, the byproduct is PPH3 doubly bonded with oxygen. Okay, so this is a pretty big mechanism, right? This reaction is also called Mitsunobu reaction. So the reaction name is Mitsunobu reaction. So let's quickly discuss once again. So we have an acid. We are using alcohol PPH3 and a dead molecule to make it ester. So this is the structure of dead molecule. So PPH3 with its lone pair will attack at this nitrogen, and this double bond nitrogen will get a negative charge here. Now acid will come, and this nitrogen with its negative charge will grab this acidic proton, will generate a carboxylate anion. Okay, and then in next step alcohol will come, and this oxygen lone pair will bond with phosphorus and will break this bond, and this bond pair will fall on nitrogen atom. And this nitrogen atom will get proton neutralizing oxygen, and you generate this molecule and this corresponding byproduct. Once you have this, you are almost done. You have another carboxylate anion. So this O minus will form a bond with R, and this bond will form a double bond with phosphorus, giving me this as a side product and this as a main product. So this was the 6th method. So now let's move for the 7th method available. Okay, so for the 7th method, I have a carboxylic acid and I'm reacting it with TMS chloride and a base. So what is a TMS chloride? You need to watch my protection strategies for alcohol, my previous video, and you will be able to easily understand what is TMS chloride. So for time being, TMS chloride can be written as trimethylsilyl chloride. So in first step you need to use this molecule. This will give me A, and that will react with methanol, and that will give me B, and that B is my product. That B is my protected ester. Here R will be methyl group because I have used methanol. Okay, so we have an acid, we have a base. So this base will grab this proton, will generate a carboxylate anion, and now you have a TMS chloride. So at this point of time, this oxygen will attack at this silicon, will remove Cl group. So this will generate R C double bond O, O. I can write this whole group as TMS, that is SiMe3. Okay. Now once you have a methanol, so this oxygen lone pairs will attack at this carbonyl, and through conjugation this whole group will leave, giving me the main product O, Me, and the side product SiMe3OH. So this is the another method to convert your acid into an ester by using base with trimethylsilyl chloride in first step, and in second step methanol. If you change this methanol into ethanol, the R group will be ethyl. So by selectively you can, by changing this alcohol group, you can change your R group of ester. Okay, let's see the next method. So I have a carboxylic acid and I'm reacting it with a alkene. The alkene here is this one, and I also need acidic condition to do this reaction, and the product is this particular product. So feel free to pause the video and try the mechanism by yourself. Okay, so we have alkene under acidic medium. This double bond will grab this proton and will generate this very stable tertiary carbocation. Now it is very clear you have a carbocation and you have an oxygen bearing not negative charge, lone pair here. So this oxygen is going to form a bond with this carbocation. And this is how this oxygen is bonded with this particular group. And later that hydrogen can be removed by water molecule present. This hydrogen can be later, let me write it. So we have H plus here. Water can come, can act as a base, can take away this proton, giving me the final product. So this is the another method for protection. Okay, I want to talk something important. Suppose I have a carbonyl system, a alpha beta unsaturated carbonyl system, and if I react it with a Grignard reagent, so we know that Grignard reagent is very strong and it will do the 1,2 addition selectively. But if you want to add your Grignard to the 4th position, then you need to think about something called BHT or BHA. So this is very important. You need to know this. This might show up in your exam. So we know that Grignard is usually does 1,2 addition. But if you want to do 1,4 addition of Grignard, you need to think about BHT and BHA. So what is a BHT and BHA? So BHT can be written as butylated hydroxy toluene, and BHA is nothing but butylated hydroxy anisole. So what is the structure of BHT? So we have a toluene, as name suggests. Okay, I have a toluene, and we have a hydroxy group at 4th position, and we have a butylated version of it. So this part is a butylated and this part is butylated. So this is the structure of BHT. And what is the structure of BHA? So it is straightforward. Just instead of toluene you have to take anisole. So the structure will be, here we have a anisole, that will be OCH3. Rest will be same. So this is my BHA, that is butylated hydroxy anisole. So let me give you one example to make you understand that how by using BHT and BHA you can force your Grignard to add at 4th position. Okay. So let me give you one example. Okay, let's say I have BHA. So let me draw BHA. I'm purposely writing this as OH. So this is my BHT. Let me start with BHT. So this is my BHT. If I use base like butyl lithium, so butyl lithium is nothing but the 4th carbon, 4 carbon base. So this will take away this proton, will generate O minus. So this will give me O minus, and we have a 3rd butyl here. If I react this molecule with Cl, C double bond O, and this particular alpha beta unsaturated acyl halide. So we know that O minus will attack at this carbonyl through conjugation. Cl is going to leave and you will generate oxygen bonded with carbonyl and this group. Now once you attach BHT or BHA to your molecule, and if you send Grignard reagent, this carbonyl feels so much hindrance that it will send Grignard reagent at the 4th position only. So it has no other choice, it has to go at 4th position because of hindrance causing by this 2 big third butyl group. Okay, so this will give me, so this goes here, and this goes here, and this will give me, for time being I'm writing this as BHT, oxygen, O minus, doubly bonded, and this alkyl group is now here. Furthermore, this will be protonated and you will get BHT O carbonyl, and you successfully added your Grignard to the 4th position by using BHT or BHA. And I want to remove this BHT or BHA. So which reagent should I use to convert into back? So this will be hydrolyzed into OH group. Okay, so to do this is a kind of deprotection, you can say, to remove this BHT or BHA group and get back your OH. So you have to use steric ammonium nitrate, that is a can. So use steric ammonium nitrate to cleave your BHT and BHA, and this is how you can form this product. So this is something important. Okay, let's talk about Oxazoline. So if I react my carboxylic acid molecule with a amine, okay, in presence of toluene as a solvent, so toluene is just acting as a solvent, and you are getting a oxazoline moiety. So this is an interesting reaction. You are reacting your acid with the amine and you are getting oxazoline. So pause the video and try the mechanism. Okay, so let's see. So this nitrogen will attack at this carbonyl and will open up this bond. So we will get, so we have OH, CH2, okay, I'm starting from here, OH, CH2, C, we have NH, now bonded with OH and OH, so we have OH and we have OH and we have CH2R group, right? This is a CH2R group. So I just connected this nitrogen with this C, converting this C double bond O into OH. Now this nitrogen lone pair will form double bond here and will eliminate this OH group. So this will give me OH, nitrogen doubly bonded with, we have CH2R and we have OH. Okay, I hope I'm clear. This is 1, 2, 3, 4, 1, 2, 3, 4. This is 5, 6. This is 5, 6. Now this 5 bond, let me write 1, 2, 3, 4, 5, 6. So 5 has CH2R and OH, CH2R and OH. Now at this position, this oxygen will attack here and this double bond will fall on nitrogen. So this will generate, so we are closing up, we are forming a ring now. So this will give me oxygen, something like this. This is 1, 2, 3 has 2 methyl group, 4 is nitrogen, 5th is my carbon, and that carbon has CH2R and OH. Now this nitrogen is bearing negative charge, so this will form double bond here, eliminating OH, and this is how you got your product. So this is 1, 2, 3, 4, 5. Okay. So react your acid and amine and generate oxazoline, and this is the mechanism. So at this position, cyclization is happening, and furthermore nitrogen with its lone pair of electron come back, will eliminate OH group, and you generate oxazoline. Okay, let's talk about orthoesters. So I'm giving you one question and I want you to solve it. I want you to predict the mechanism for it. So this is my carboxylic acid and I'm reacting it with this molecule, this particular molecule under acidic medium, or you can use Lewis acid, and this will generate. So the product is going to be, well, in first step you need this molecule, in second step you need Lewis acid, and the product is going to be, we have, product is little complicated, but the mechanism is pretty straightforward. So this is the product. So you have this particular reagent in acidic media in presence of carboxylic acid, and you are generating this particular orthoester. So pause the video and predict the mechanism. So let's begin. So we know that this acid and this alcohol, so they are going to form a ester molecule in presence of acid. We have already seen it in first step method only. So the first method to make ester was to use acid and alcohol in presence of H+, and this will generate RC double bond O. Then we have CH2. I'm just writing it in a proper orientation like this one. The exact same thing, okay? Oxygen CH2, and this whole group. Okay. Then we have a Lewis acid in the second step. So that Lewis acid will do chelation with this oxygen and will give positive charge to it. So that, well, it can do Lewis acid chelation with this oxygen also and can give positive charge here. So what do you think? Which one is going to be? Well, this particular system is under strain. It is a 4-membered ring and it wants to get open. This ring is under strain. So that's why this will be preferred. So we have Lewis acid here, and this one is positively charged now. So we have this. I can write this as like oxygen Lewis acid bearing positive, and we have C double bond O R, exact same thing. Okay. So now this ring will get open. That's why we chelated it with Lewis acid. So this will attack here and this will open up, right? So this will give me, I'm writing it here. So this will give me oxygen, and we have C double bond O R, this one, and CH2. This will be hydrolyzed into OH, and now we have this one. Okay, so this oxygen I bonded with this carbon and I broke this bond. and here we have CH2OH, CH2OH. Now furthermore, we have a reactive carboxyl group. Okay, we have a reactive carbonyl group, and we have a nucleophile. So it will attack here, and this will get neutralized. And guess what? We got the product. Right? So let me number them. So this is my 1, 1, 2, 2, 3, 3, 4. This is 4. Okay. 1 is attached to, let's say, 5. 5 has one methyl 6, and this 5 is also attached to 7CH2, that 7 has O, 8, and that 8 is now bonded with 3. We have 8 bonded with 3. Now this, let's say this 5 is bonded with A, 5 is bonded with A, this A is bonded with oxygen B, this A is bonded with oxygen B. We got the product. Quite interesting. Okay, so now let's talk about alkyne. So alkyne is a triple bond. Okay, so this is a alkyne. This is a carbon, this is a carbon, this is a carbon, and this is a carbon. Now this is a terminal alkyne. Excuse me, this is an internal alkyne. For a terminal alkyne, you will have hydrogen at the end. So this C is bonded with hydrogen. So this is a terminal alkyne. Okay, this is a terminal alkyne. The internal alkyne will be carbon or CH3 at the end. So why we need to protect alkyne? Well, this terminal alkyne hydrogen can get deprotonated. So this is the first reason why we need to protect alkyne. And the second reason is this double bond can react. So to avoid it to react, to protect it from reacting, we need to protect alkyne. So let's talk about protection of terminal alkyne. So suppose I have RCH2 C triple bond C H. So this is a terminal alkyne, and I need to react it with a base, for example methyl lithium or butyl lithium. So this base will grab this proton and will generate a carboanion. So we have generated a carboanion. Now you react it with trimethylsilyl chloride. So this carbon will attack at silyl, will eliminate chloride, and this will give me RCH2 C triple bond C TMS, that is nothing but SiMe3. Well, we protected the alkyne with SiMe3. So this is the protection. This is how you can protect your terminal alkyne. First, grab this proton. Second, react it with any silyl chloride, and this is how you protect it. And if you want to deprotect, you have to guess it. I have already discussed it in my previous video of protection and deprotection of alcohols. So to remove silyl group, you need a F- source. Okay, you can use TBAF, tetrabutyl ammonium fluoride, and you will get back your hydrogen at that position, and this will be leave out as fluorine bonded with SiMe3. So this is the protection for terminal alkyne and deprotection. Now let's talk about the internal alkynes. Okay, suppose I have an internal alkyne, this particular alkyne. So to protect this one, you have to use a inorganic complex of cobalt. that is CO2, CO8. Well, this CO is cobalt and this CO is carbon monoxide. So you need to use this particular inorganic compound to protect your internal alkyne. And how does it protect it? All it's doing is forming a complex with my alkyne. Now see the difference. Here we have 8 carbon monoxide, here we have 6, simply because now this cobalt has formed complex with the alkyne with hapticity of 2. Okay, it does some sort of chelation, you just need to remember that, and this is how it protects the alkyne. And now this alkyne bond will not do reaction, and this is how you block it. And how to deprotect it? You can use Fe plus 3 salt like ferric nitrate, or you can use steric ammonium nitrate also, and you will generate your alkyne back. So this is the protection for internal alkyne, where you need to use this particular inorganic inorganic complex, and this is how it generates the protected version. And to deprotect, use Fe plus 3 salt or steric ammonium nitrate, and you will get back your product. So based on this, I'm going to give you one question now. Okay, so let's say I have a starting material, a double bond, a triple bond. This is a carbon, this is another carbon, and we have this. So we have a double bond and we have a triple bond. In first step, I am reacting it with this cobalt salt in presence of diethyl ether, and I am getting A. Then this A reacts with first step BH3, second step NaOH in presence of H2O2, hydrogen peroxide, and you are getting B. And then this B reacts with ferric nitrate, and this gives me final product C. So pause the video and draw the structure of A, B and C. Okay, so this is a protection strategy to protect alkyne, simply because if you do anything to this molecule, triple bond will react first instead of double bond. So if you want to react your double bond first and not the triple bond, you need to protect it. So we protected it by using this particular reagent, and the structure of A will be so this is now bonded with CO2, CO6, not 8, 6. Okay, so now this is blocked. Now I can react my double bond. So triple bond is more reactive than double bond, but I protected it. So now I can react it with my double bond. So first step BH3, second step NaOH H2O2. This is a hydroboration oxidation reaction, which we will discuss in detail in future when we will talk about reagents. For time being, you just remember, you need to add water molecule in a double bond in an anti-Markovnikov rule. What is the anti-Markovnikov rule? You need to add your negative part of the reagent to that part which has more hydrogen across double bond. So across double bond, we have 2 hydrogen here and we have 0 hydrogen here. So we have 0 hydrogen here and 2 hydrogen here. So anti-Markovnikov rule says add your negative part of the molecule. So this is a water, this is a negative part, this is a positive part. So I'm going to add my negative part to the the carbon containing more hydrogens. So this will give me, and you have to remove this double bond. So I'm adding my OH negative part to the carbon which has 2 hydrogen, that is more hydrogens. Okay, and 1 hydrogen is added here. And this is still protected. Okay, and finally to get the structure of C, you are deprotecting your alkyne by using ferric salt. And now the triple bond is free to react. So this is the structure of A, this is the structure of P, and this is the structure of C. Okay, so a quick flashback. Whatever we have discussed till now in protection and deprotection. We discussed about amines. We solved problem based on that. We discussed about alcohols. We solved problems based on that. We discussed for diols also. We discussed for aldehyde and ketone. We discussed for carboxylic acid. And we also discussed for alkynes. So up to my knowledge, I have discussed everything when it comes to protection and deprotection of organic molecules. And we have also solved practice problems for all of them. So that was the series of protection and deprotection in organic chemistry. I hope you liked it. Feel free to ask me any question if you have, and do subscribe. Thank you.